So good morning. Thank you for joining this class. As we had agreed earlier on, we weren't able to have our live class, so we agreed that I record and send the video to you. So that's exactly what I will be doing. So far we have discussed the first, second and third lesson, and that is what I'm displaying here. As you can see, we've already looked at overview and the terms which are used in computer graphics. We have also looked at the mathematical background. This is going to be very important. In fact, a bulk of computer graphics consists of computations, especially matrix and vector algebra. Then you have OpenGL programming, which we introduced ourselves in the third lesson. We had a look at the graphics library utility toolkit. We were looking for a platform where we can have examples and make use of those examples. And we discovered that it can be a little bit tricky if we went the way of using code blocks, for instance, and therefore we opted for WebGL, which is standard and everybody can access it because of course it's online. As long as it's not even online, I mean as long as your browser is enabled, then you can go ahead and do it. Today I would like us to discuss lesson 4. We started it last time when we identified that we are going to be using WebGL, and therefore we had to introduce ourselves first to WebGL. And in our introduction to WebGL, we first of all looked at how we connect our browser to WebGL by first of all creating a canvas within the HTML page and then contextualizing that canvas so that within that canvas with WebGL, so that within that canvas we can invoke WebGL functions, and we're able to do that. And from there we did draw a simple 2D shape. It was a square, and able to display that square. I shared those files with you and you're able to edit them, and then I gave you a quiz. Most of you attempted the quiz, and I think 25 of you attempted the quiz, and the results I was able to mark, and the results are as displayed here. Well, that was it. So today I would like us to proceed from there. I want to believe that everyone now, having looked at the work you did, that majority of you now can be able to work with WebGL. If you still have challenges working with WebGL, please revisit these videos here, listen to them, try out what they are displaying, and then join us as we discuss curves. Lesson 4, we discuss curves in WebGL or in OpenGL. There are several ways in which curves. There are several types of curves in WebGL, but anything that we can have parametric curves, we can have ellipses, we can have polygons. All these can generally be referred to as curves. Parametric curves are basically curves which are derived from parametric functions. We refer to them as curves generally, and we have the equations that can generate them. We have the independent variable SAT subjected to a certain function yields XYZ, which are the coordinates now that define the curve. And we can use Bezier curves and surfaces, which was developed by French engineer Pierre Bezier, in order for us to draw the curves. OpenGL provides these Bezier functionalities for drawing of Bezier curves. The so-called Bezier curves have properties such as they always passes through the first control point and the last control point, and they lie within the convex hull of the control points, and the Bezier blending function is always positive, greater than 0, you can put it that way. The ellipses basically are defined as a set of points such that the sum of the distance from the two fixed positions, that is 4c, is the same from all points. In other words, when you have an ellipse, is a plane curve surrounding two focal points, such that these two focal points, if the distance from those two focal points is measured to the ellipse itself, then the sum of the two is always constant, and that is what this property is basically defining here. And then the ellipse also has major axis, which is a straight line segment passing through both foci and extending up to the boundary of both sides. It has a minor axis that spans the shortest dimension ellipse and bisects the major axis at right angle into two equal halves. Sometimes you can obtain the midpoint using the modified Brenham's algorithm, midpoint of ellipse algorithm, by using the based on the Brenham's algorithm. The advantages of using it is because it simplifies the process, and of course faster implementation in processors. The simultaneous calculation of pixel positions with parallel processors is also an additional advantage. Polygons, basically we have seen the curves, we have seen the ellipses. When you talk of a polygon, we are talking of a graphic with several vertices. In other words, it has several corners, if you may put it that way. And these corners basically define the edges. Sometimes we talk of 4 sides, then we call it a square, a rectangle, 3 sides a triangle. When you talk of polygons, they are beyond that. As long as these internal angles are non-convex, are convex in the sense that they are not greater than 180 degrees. OpenGL does not deal with concave polygons. Surface and we can therefore, in fact, it is hard to think of a polygon where the internal angles are greater than 180 degrees. When you're dealing with polygons, we come across terms such as surface normal, which means that if we have a surface, let's say, in fact, you can think of it of a triangle or any polygon, so to say, the vector perpendicular to the plane that defines that polygon is what you're referring to as the surface normal. If you want to find the surface normal, which is required, we basically carry out what we call cross product of the surface and then we get the surface normal. When you have several polygons put up together, some of them have their vertices visible, others they are hidden, then we talk of the polygon soup. And we want to avoid a scenario where we actually even include vertices which are hidden and parts which are hidden within the polygon soup within the diagram. This is a waste of storage space. It also leads to a loss of semantics and leads to brute force lettering, which makes interaction with the model complex. To avoid that, then we can make use of we can try to simplify that, and we have a function, an algorithm which is used to hide the surface, to remove the hidden surface. So we use this algorithm displayed here to remove that. Those which are visible to the eye, which are closer to the eye, surfaces which are closer to the eye, are actually not displayed. The ones displayed, but those ones which are far and are hidden are actually removed, so that then that makes it lighter. Other terms that you come across when you're dealing with polygons include meshes, which are linked groups of polygons which can be used to present surfaces. Triangle strips, which are a collection of linked triangles. Triangle fans, which are a collection of linked triangles that share a same vertex. Quadrilateral strips, which are basically a collection of linked quadrilaterals. And then we have, of course, terms such as scan conversion, which is a process of converting polygons edges in coordinates into lines to display on a screen. Then when you want to scan convert a line, we sample the true geometry of the line and approximate it using the nearest pixel available. If you want to scan convert a polygon, then we have got to play around with these coordinates. The x and y coordinates would correspond to a pixel position, whereas the z coordinate would measure the vertex distance from the eye. And then of course we have the sweep line algorithm, which steps down a pair of edges, starting with this. If you can, for instance, say x and y coordinates, then it could start with x1, y1, and then goes down scale line by scale line, scan line by scan line, finding the start and the end of the part of the scan line inside the triangle. This algorithm is efficient because we only need to compute the gradients of the edges px and qx once at the beginning. The rest will be done by the loop. So we've just discussed hidden surface removal, and we have seen it's necessary where we have a polygon soup to avoid the ugly scenario of having to use that excess memory resources just to hold a polygon whereas we have some hidden parts of it. And you want to render curved surfaces in curves in OpenGL, be they curves, plain curves like Bezier curves, or be they ellipses, or be they polygons, then we will come across functions such as GL map, GL enable, evaluate coordinate, GL begin and GL end. Display function is used to show the polygon, GL vertex, and of course you can see that GL map takes a number of coordinates that define the polygon. But in OpenGL, in WebGL, we can basically follow the same. We can basically follow what we did last time. I had created a file to illustrate that. Basically, there are 3 files. If you want to draw the curve, you can see I'll add this to whatever resources you had last time so that you can download it. We have WebGL draw curve.html is one that renders on the browser, and basically is what we have here. This is what it renders. We have the context, and then we have the triangle, and you have a curve inside that triangle. So that is implemented by this code you're seeing here. And of course this code is we are not foreigners to it. So for instance, we need the HTML file. We separate the HTML from the CSS and from the JavaScript file because we don't want to have one very long and code that is not readable. So for instance, here you can see how we bring in the CSS after we have defined it in this file. The solid black boundary you're seeing is what you're seeing here. Solid black boundary. Of course, now we have the rest is the context, and therefore the color black is not in the context because it has been contextualized to have gray, which is visible, of course. Then we have within the body we have the canvas, which now we can see is this gray section here, the canvas, and within which we find now the triangle, and of course the curve. And we have also the script, the JavaScript, which now defines WebGL draw curve.js, which now defines the functions that eventually affect the drawing. By calling the WebGL functions, we are able to draw now the triangle and the curve. Here we see the code that defines the triangle and basically the curve. We have the create program is invoked, and of course we provide the create shader. We create these shaders. Remember, we have 2 shaders. One is for the vertex shading, and the other one is for fragment shading. We had discussed that in the previous exercise. And within that we have the vertex source and also the fragment source, defining the various dimensions. And from there we are able to create program, the shader program, so to say, and define the canvas. Of course, the canvas is the first thing to be defined. If it's not defined, then you have a way of reporting that this browser does not support. In this case, I don't think you have included that does not support the OpenGL, but we're assuming that if the browser supports, then this will be executed. The program will be created and will be used, of course, with the vertex being enabled, and then we'll have the buffers created, the vertex buffers being created, and once they are created, then it's just a matter of drawing or displaying it on the screen. This is the JavaScript code that will be used for purposes of rendering the WebGL curves, which effect we can see here. I will be uploading this, and I will request you to run through it and see whether you can change some of the colors like you have done to the others. The reason why we do such simple exercises is so that we can improve, we can confirm that we have actually understood or at least we have gone through the code itself. Now, having said that, I think you'll be in a good position to edit and also read for yourself the content of this particular lesson 4. any questions, we can respond to them in the forum. Thank you very much, and I hope this was a helpful video was helpful to you. Thank you.